Thank you very much for the introduction, and thank you very much for the invitation. So it is my first experience to cross the equator. Okay, so this is today I would like to talk about some recent progress of analytic torsion invariant of K3 surfaces with involution. In the 1 year ago, there was a conference in Lille, and there I talked a similar subject, and it is a kind of progress report since that time. Okay. So, as introduction, maybe 0, I start from, okay, it's okay. I would like to talk about analytic torsion of elliptic curve. So then I want to explain what I want to do in my talk today. So for tau in the complex upper half plane, I define E tau as the complex torus whose period is 1 and tau. I consider the Kähler matrix, flat Kähler matrix, gamma, so this has normalized volume 1 or 2, I forget, but yeah. Then this is a flat Kähler metric, so I consider the Laplacian. So if you, it can be expressed in explicitly by the formula so I define the zeta function of Laplacian. Zeta tau of S. This is so in this case, eigenspace of Laplacian is labeled by the pair of integers, and this origin corresponds to the 0 eigenspace, that is the space of constant functions. And then, because it is very complex torus, so it is everything can be calculated explicitly, and this is given by so-called real analytic Eisenstein series. Let me see. Over the integer. This is the eigenspace. The eigenvariable Laplacian. So this is the corresponding eigenfunction is just a certain combination of trigonometric functions. Then, so I think that it is Ray and Singer who introduced the notion of regularized determinant of Laplacian. Let me explain this notion. So if H is positive definite Hermitian matrix, of a finite dimension, then you have this formula. Log of that H is given by, maybe I forget my sign here, but just forget about this for the moment. Let me see. This is minus. So this is a zeta function of a finite dimension. So as an analog, they introduced. So this is a regularized determinant of Laplacian. It's defined as the exponential of. So this is so-called regularized. And because this real analytic Eisenstein series admits analytic continuation and it is holomorphic at the origin, so this is well defined and you get the number. This is an analog of a usual determinant. And then the classical Kronecker limit formula can be stated as follows. Well, essentially he calculated the determinant of Laplacian. This is given by the norm of the Dedekind zeta function, but up to some 4 and 4 also. So, of course, eta tau is this is a Dedekind zeta function. And eta tau to 24th. So this is a so-called Peterson norm, and this is a modular form of weight 12. So so this is a definition of the Peterson norm. So this is so-called Kronecker's limit formula. If you formulate in a certain way, then this is a statement. But by Polyakov anomaly formula, we can also formulate as follows. So I set tau L of E as the product of volume E gamma and the determinant of Laplacian to the power -1, and I also must multiply some so-called anomaly term, that is E log let me check the sign. Okay. So here I following the convention in Arakelov geometry, to define the volume I multiply 1 over 2 pi. So I introduce this number. Then this tau L E. Now, so if so here I do not assume gamma to be flat. So gamma is not necessarily flat in this definition. So, but even though by the anomaly formula of Polyakov, one can prove that this is independent of the choice of scalar metric gamma. And so if you use the flat metric, this one, then this quantity coincides with the more or less this one, because this has normalized volume. So then and tau L E is given by 4 something like this.
Gamma, you get also different Laplacian.
Exactly. So
So they cancel.
yes. So this is a factor which computes the difference of flat Laplacian and non-flat Laplacian with respect to non-flat metric. I think that's okay. So this is a most basic or primitive version of what I want to talk today. So I want to generalize or extend to K3 surfaces. So I introduce an invariant using kind of regularized determinant that is so-called analytic torsion, and I construct an invariant. Then if once I get an invariant that gives rise to a function on the moduli space, and moduli space so K3 surfaces with involution. And as Klaus explained us yesterday, well, Enrique's surface, precisely speaking, its universal covering K3 surface is a particular example of K3 surface with involution. And a lot of things, a lot of properties of those K3 surfaces with involution can be extended to arbitrary K3 surfaces with involution, and it's modularized, for example, modularized spaces will be arithmetic modular variety of orthogonal type. And then this way we will get a function on the orthogonal modular variety, and then I give you a formula for that invariant, analytic torsion invariant. Later, I'll give you a very explicit formula, and that will be given by the product of Borcherds T function and classical Ziegler modular forms. So, okay. But I forget, so maybe I should write here. So this is a joint work. Ma, Shohei Ma. He is unfortunately not, that not yet appeared. Okay. So let me define what is K3 surfaces with involution. So a pair x iota where x is a K3 surface and iota antisymplectic holomorphic involution is called a two-elementary K3 surface. So because I explain immediately why it is two-elementary, it is more or less a two-elementary lattice polarized K3 surface. So this is the reason that why I call this two-elementary. And the type of the pair x iota is defined as the isometry class of the lattice H2xz plus O. So this is the invariant or plus one eigen sublattice of the second integral cohomology. So this is equipped with the cup product. This is a lattice. So this the isometry class of this lattice is called the type. So in 80s, Nikulin studied these K3 surfaces in detail. So let me recall some of his results. But before doing this, just let me fix some notation. So because X is a K3 surface, I introduce the K3 lattice as but my E8 is negative definite. So U is a hyperbolic, usual hyperbolic plane, and E8 is negative. E8 lattice. So this is a K3 lattice, and the isometry is called marking. Then so I set M as the image of this H2xz plus. Then so early results of Nikulin can be stated as follows. First of all, M is primitive, two-elementary, Lorentzian, sublattice, of the K3 lattice. So this is, yes, so here, as I said, there appears the two elementary lattice. So in some sense, the pair X iota is two elementary lattice polarized in this sense. And the second, the deformation type of X iota is determined by the type M. So the type, in fact, is a deformation type of the pair. I mean, smooth deformation type. Yes. So that is exactly the different distinction between the notion of lattice polarized K3 surfaces in the sense of Dolgachev and this one. But the type, the symmetry class M is determined by the triple R, L, delta, where R is just Z rank of M. And because M is two elementary, so L is rank of this discriminant group. Maybe let me write discriminant group A of AM. AM is, so this is a discriminant group, and delta so delta is a parity of the discriminant form. AM. So this triple determines the isometric class. And Nikurin classified all of them. So there are 75 types. 75. That means that there are 75 different deformation types of K3 surfaces with involution. Okay, then how the moduli space is can be described. So for this, I introduced a set I define lambda to be the orthogonal complement of M in the K3 lattice. So yesterday it was written as N, but I use lambda for this lattice. So, okay, and then in what follows, R is always the rank of M. Then signature of lambda is 2, 20 minus r. So we have a domain omega lambda. So this is two copies of Hermitian domain of type 4. Type 4 domain. And their dimension is 20 minus r. So, well, one has the following. So the dimension, so this is the dimension, so every value of this range can be realized as a dimension of this omega lambda. And so this is a period domain. So I define omega lambda 0 as a so this is d lambda is a discriminant divisor or so as yesterday HD is a hyperplane defined by the root D. So I remove, to get moduli space, I have to remove this discriminant divisor. And I define m lambda 0 as a quotient. So this is a Zariski open subset of orthogonal modular variety of dimension 20 minus r. Then the period. So now assume that x iota is of type M. Then there is some isometry such that alpha H2 xz minus is lambda. So that means that, well, and the canonical form. Canonical form is, because I assume that involution is anti-symplectic, this means that this lies in the anti-invariant subspace. So, which means that this determines the point of this projective space, but we have Riemann-Hodge bilinear relations. So, and to kill the choice of this marking, the period. So, if I consider the point, the corresponding point, so this big bracket means that I take O lambda orbit of this point. Then we get a point of this orthogonal modular variety, and in fact we can prove that this point omit the discriminant divisor. So this point is called a period. Of the pair x iota. Then as in the case of Enriquez surface, we can prove that the modular space of two elementary K3 surfaces type M is isomorphic to omega lambda 0 via the period map. So far everything is quite parallel to the story of Enriquez surfaces. Basically, there is nothing new. Now, but here there is something new. So that is the Torelli map. Because in general, I consider K3 surface with involution. So the involution in general has fixed points. So Nikulin also classifies the topological type of involution. So for the pair x iota, I denote by x iota as a set of fixed points. So let me recall some results of Nikulin again. So, so he classifies a possible topological type of x iota. If, well, okay, maybe I can. X iota is then either empty or the disjoint union of two curves, or maybe I should write this way. So this is if so depending on the type of the lattice, type of the involution, the set of fixed points is classified in this way. So we have basically three possibilities, and this what is this here? So where CG is a curve of genus G. EI is a smooth rational curve, and G is given by this formula, and K is given by this formula. So except these two cases, the fixed point set consists of a unique curve of higher genus, and all the others are just P1. I think that if this is divisible by 2 in this cohomology, then that means that if I understand correctly, that condition is equivalent that the delta is equal to 0. So, okay, I define the Torelli map. This is the Torelli map is basically the map assigning the pair x iota the period of the fixed points, fixed curve. So for this, I introduce notation. So this is a bigger modular variety of degree G. So Torelli map the Torelli map Jm is defined by so this omega x iota is the period. So this case may be this, well, for the moment, I do not define Torelli map when the fixed point is empty. When it consists of two elliptic curves, then I regard that these are the degenerate curve of genus 2, and I understand this way. So if I understand this way, then this formula also makes sense. This is just a total genus, formula for the total genus. And in fact, this also, well, if I also define in this case G. In this case, I define G to be 1. If it is, this is empty, but I define its genus to be 1. So in that case, there is no meaning of genus anymore, but for that lattice, I still use this definition.
For the last case, not the rational curve.
because there is no period of rational curves. So.
You do not go to the boundary of AG.
Yeah, because this map, it is, yeah, for the moment, I do not consider it. So, because of the existence of fixed points, we have another player that is the Rayleigh map. So now I want to introduce my analytic torsion invariant. Okay. Should I take a break or it's okay?
You're the one most likely to feel the need of a break.
Myself, I'm.
Stay here, we seem to know you.
It's okay. Okay, then let me continue. So in the first part, I introduced invariant of elliptic curve using determinant of Laplacian. So I mimic that construction in some sense. So for that, I have to maybe for the audience today, the notion of analytic torsion or equivariant analytic torsion is not so common. So let me recall what is analytic torsion. So this notion was introduced by Ray Singer in early 70s. They generalized the notion of so-called Reidemeister torsion, Reidemeister-Franz torsion in topology to the Doam complex. So it is a kind of infinite dimensional version of that one. And let me explain what it is. So to explain this, I just forget about K3 surface. So I start a compact Kähler manifold. For simplicity, so today I always consider involution as a group acting on the manifold. Preserving I consider involution that preserves the Kähler metric gamma. Then I consider the Laplacian. Because it is metrized, so you can consider the adjoint of the Deeper operator, and which acts on the space of 0Q forms on V. And then you get a spectral zeta function. I don't have space now. So the spectral zeta function. So this is a set of eigenvalues of Laplacian, but I have to remove the zero eigenvalue and to lambda to minus s, but I have to multiply the multiplicity of the eigenspace. So this is eigenspace. with eigenvalue lambda. So this is a spectral zeta function, and it's equivariant zeta function, or kind of L function. I use the theta, so okay. So this is, instead of taking dimension, I consider the trace of the theta action on the eigenspace. Because
dimension E plus minus E minus.
Dimension.
So you have this eigenspace E?
Yes.
Because it's the plus and minus.
Yes, yes. So because theta is involution, so its eigenvalue is either 1 or minus 1. Yes, exactly as you say. And this is possible because by the assumption that theta preserves a metric, so theta this condition implies that theta also commutes with Laplacian. So theta acts on eigenspace. So this is the equivalent version. So I consider today only the involution, but if you consider the group action which preserves the metrics, you can proceed in the quite similar way. Then I define the analytic torsion. So this is due to, I think, Ray-Singer. But in more general setting, this is due to Bismuth-Gilles-Frey. So what is this? This is by definition tau v gamma is defined as the exponential of minus ds so I forget q here. This is simply constant. So. If you just forget about this factor, then this is just a regularized determinant of Laplacian. So this is a weighted alternating sum of. If I can also write this way. So it is a weighted alternating product of the regularized determinant of Laplacian. And its equivariant version, V2 equivariant version, is defined in a quite similar way. Oops. So I don't need prime here. So maybe I should mention that this zeta function, I should mention here that both these zeta function converges if the real part of S is bigger than a dimension, complex dimension of V. and extends to a meromorphic function. So extends meromorphically to the whole complex plane and holomorphic at the origin. So this definition makes sense. Because functionally, if you want functional equation, I think that manifold should have large symmetry. Otherwise, you cannot expect such symmetry. You mean symmetry with respect to some line. For example, in Riemann zeta function, you have symmetry with respect to this line, but in general, there is no such symmetry anymore. This is to extend this one, we use the so-called heat trace expand. So So this zeta function is expressed as the Mellon transformation of the trace of the heat kernel. And so the problem is reduced to the existence of the short time asymptotic expansion of the heat kernel. So the simplest case is this one. If I remember correctly, so this is something like this. So it's something like this. So we have a formula like this, and and by this formula we have we separate the integral into these two parts, and this part is already holomorphic for any S, but so what we have to take care is this part, and here we use asymptotic expansion. Trace of E2 minus T box 0Q has asymptotic expansion like this. T2 minus n is a complex dimension. So using this, we can prove that it admits analytic continuation. Okay. So this is a general definition of analytic torsion and equivalent analytic torsion, and it is, I think, Bismuth who discovered that this notion is related to the so-called Grothendieck-Riemann-Loch theorem. And so this is, and that part I use, that theory to construct invariant. So this is general theory. So now let me return to the case of K3 surface with involution. This is a two-elementary K3 surface of type M. So I want to construct an invariant of the pair using equivariant analytic torsion of x iota and also the analytic torsion of fixed points. So I choose gamma as a iota invariant Kähler form, and I also choose eta non-zero canonical form. Then I introduce a number tau m as a product of this is, I think, 14 minus r. Okay. So let me check the sign here. This is minus sign. Yeah, so here, so this is, in general, X iota consists of several components. So this volume and the torsion are assumed to be multiplicative with respect to the decomposition into connected components. So, if X iota is empty, then they should be 1. Ah, yeah. Okay, irreducible decomposition. So, well, at the first glance, it's maybe, well, it's maybe you do not, well, it's not so clean, at least. But if the metric is Ricci flat, this term disappears. This term is simply 1. So because the condition that the metric is Ricci flat is that this quantity is identically equals to the constant 1. So if the metric is Ricci flat, this factor disappears. And so this is essentially the product of equivariant torsion of the K3 surface with involution and the analytic torsion of fixed points.
What about for the empty set, you said it is 1?
Yes.
And for rational curve?
That depends on the choice of metric. So it can be, if you deform the metric, if you change the metric, this number also changes. But with this factor, and volume, then in fact this number is independent of the choice of matrix. That is the first result. So in the introduction, I mentioned the Polyakov anomaly formula, the role of Polyakov anomaly formula. That factor is exactly the same. The role of that factor is exactly the same. This tau mx iota is independent of the choices of the metric gamma and canonical form eta. So that means that tau m is regarded as viewed as a function of the moduli space m lambda 0. So this is a function that I want to understand today. And this, in fact, this tau m is the main component of the so-called string amplitude at genus 1. For Calabian 3/4 of Borcherds. So this has, precisely speaking, in B model. So this has some physical meaning. So it has, so this function is related to genus 1 mirror symmetry. But maybe today I do not have time to talk about that. But this invariant has that background. Okay, so this is a construction of invariant, and as I mentioned, this invariant, this function, is expressed by using very explicit Borcherds product and very classical Ziegler modular forms. And I want to explain those automorphic forms now. To explain the Borcherds product, I have to introduce some elliptic modular forms. So here lambda is again two elementary lattice, even lattice, and signature 2, n. Now I do not assume lambda is a primitive sublattice of the K3 lattice. Just forget about this. And for this, if you are given such a lattice, I associate in a canonical way vector valued elliptic modular form of type rho lambda. Rho lambda is a very representation. My construction is as follows. So for this, I already introduced this is the Dedekind zeta function. And I also need the theta series of the A1 lattice, that is this one. So they are modular forms for certain groups, and okay, using these modular forms, I have to construct. I construct a vector valued modular form in the following way. So I set phi lambda tau as tau to minus 8, 2 tau to 8, 4 tau to minus 8, and theta A1 to tau to, I think, R lambda to n minus 10. Just let me check. Okay, just let me write this way. Okay, so phi k. I define phi k this way. So my collaborator just arrived now.
Just in time.
So this is a modular form for gamma 04. And using this one, I want to induce a vector valued modular form. I follow the method of Borcherds. What he suggests is as follows. So I define f lambda tau as this number. I should be careful here. This is a 10 minus n. Okay.
But then the weight must be 10 minus n.
Yes. In this one?
Yeah.
Yes. And because the signature 2 comma, and let me see, this is, maybe something's wrong here. This phi 10 minus, no, it has weight, this has weight minus 4. So this has weight, phi k has weight minus 4 plus k.
No, divided by 2.
Yes.
Also.
So this phi lambda so this is a Weyl representation. And this board E gamma, where gamma runs over A of lambda, A lambda, the basis, the standard basis. Of the group ring. So I define this way then. Oops. I can prove that this f lambda is elliptic modular form of type rho lambda and with weight 1 minus half of n, I think. So we can consider it's Borcherds lift. But for that, I need the condition that this has integral Fourier coefficients. And if now, from now, I assume that lambda comes from K3 surface with involution, then in general, the Fourier coefficients of this one is not integral, but 2 to g minus 1 f lambda has integral Fourier expansions. So I can consider the Borcherds lift of this one. For example, if G is, for example, if I understand correctly, no. If the rank, I think the rank of the rank of lambda is bigger than 16 or 17, I forget. Then it really has there is really a non-integral Fourier coefficient. So to kill that part, this non-integrality, I have to multiply this number. So I have a Borcherds product. So this is an automorphic form. So in this case, the full orthogonal group of certain weight. I do not write the formula for the weight. It's a bit complicated. And I also need some Ziegler modular forms. I think that it should have character plus minus 1. So to express our invariant, I use two kinds of Ziegler modular forms. So theta a b tau, even theta constants. So this is, maybe I use omega for the period of curve. So this is sum let me check if I am correct. Yes. So this is a classical Riemann theta constant. And so this is so here omega, the point of a Ziegler upper half space of degree G. And I introduced two kinds of Ziegler modular form for the full Ziegler modular groups. The first one is chi G. Chi G is defined as the product of all even theta constants. Well, if G is bigger than or equal to 3, this one is honest Ziegler modular forms. But if G is either 1 or 2, you have maybe it's 8th power is a honest Ziegler modular form. So just forget about this. So I also introduced epsilon omega as this one. So this is you can also this is largest. It's a symmetric polynomial in the even theta constants of the largest degree, and this is also a symmetric polynomial in the even theta constants. Precisely speaking, 8th power of the even theta constant of the next degree. And for that reason, this is also a Ziegler modular form. And the following fact is important for us. If C is a curve of genus, then C has an effective half canonical, even half canonical bundle, and effective even half canonical bundle if and only if this chi G vanishes. And C has two, at least two, has at least two effective even half canonical bundle if and only if and only if these two Ziegler modular form vanishes. So this property plays a very crucial role. So these two modular forms, Ziegler modular form more or less characterizes the loci of curves with effective even theta characteristics. Now I have 5 minutes left, so formula. Okay, so just recall the definition. So M is this is a primitive, two-elementary Lorentzian lattice, and lambda is an orthogonal complement of M.
But this is true in general for any primitive elementary Lorentzian lattice in there, or only for those coming from the same?
Yes, I think it's the same, because this is the surjectivity of the period map for K3 surfaces. So the theorem is as follows. Oops. So if so R is a rank of M so as a function of the moduli space of K3 surfaces, the two-elementary K3 surfaces, this is expressed as follows. Okay. I need some power here. Tau m to minus 2g plus 1 is, so this is some universal constant depending only on the lattice M. So this is a Borcherds product. So this is the Peterson norm as before. So this Jm is a Torelli map. So this is a major case. There are, I think that 67 cases. The analytic torsion invariant is expressed by the product of these two modular forms. This is Borcherds product, and this is Ziegler modular forms. And if R delta is 10, 0, then tau m to minus 2g minus 1, 2g plus 2 is equal to constant and the same Borcherds product, but the power is a bit different. So here only the coefficient of f lambda is 2 times 2 to the g minus 1, but here the coefficient is slightly different. Times here I have epsilon. Where if Enrique's case, there is no geometric meaning for this part, so I just put this one to be 1. And the last case is in this case, then M is either a hyperbolic plane or U of 2. And tau M this one is equal to Cm okay. This is so here, what is this F lambda? F lambda is equal to theta to the E8 lattice over eta to 24 when M is hyperbolic plane. In this case, is easier. And this the next so yeah, when so for the case M is equal to U of 2. Okay, so this is a formula. So I'm sorry that I just exhausted. I think it's the time that yeah. Okay, I'm sorry that I have no time to explain how to prove this result, but so this is a result for the analytic torsion invariant, and this is a kind of generalization of the Kronecker limit formula in dimension 2. And this is related to the so-called, as I wrote before, genus 1 string amplitude in B model of Calabi-Yau 3-fold of Borcherds boson. This is one factor. This F1 for the Borcherds boson 3-fold is this tau m times norm of the Dedekind zeta function. So this also gives the exact formula for the genus 1 string amplitude for Borcherds boson's Calabi-Yau 3-folds. Okay.